This video will cover the following learning outcomes. We're going to look into the photoelectric effect in detail and define two really important terms, the work function and threshold frequency. We'll also look at the photoelectric effect equation, which is this one here, which is absolutely essential for the exam. We'll look at the graphical representation of this process and then consider the kinetic energy of the electrons and the intensity as well. To do this, we're going to have to consider a more precise method of looking at the electrons released. In the previous lesson, we looked at the gold leaf electroscope, which is great because it demonstrates the photoelectric effect, but there's no data. We can't measure the energy of the electrons or the number of electrons. So to do this, we're going to use a photocell circuit. And the next slide will take through some of the key aspects of the photocell circuit. So this is the photoelectric effect simulation. What we're looking at is what's called a photocell circuit. So this allows us not just to visualize the photoelectric effect happening, but also to measure the currents. So we can actually measure the number of electrons being emitted. So at the moment the light is switched off and we're on visible light, and we have a target plate over here of zinc. So let's turn the light on. So at the moment we've got a visible light. We can change the color if we want to, and nothing happens at all as expected. And we can see that nothing is happening. There's no electrons being emitted and the current is zero, so that's quite important there. What we said before is that bright white light has no effect. So if I increase the intensity of visible light, it has no effect. So that's actually quite important. So let's reduce that back down to a medium intensity. What I need to do with a zinc plate is increase the frequency. So we go all the way up to violet and then we go into ultraviolet. And at some point the frequency is sufficient to release electrons from the zinc target metal. So we can see that electrons are being released and we can detect a current here, and with that we can actually calculate the number of electrons being released per second. Now really important here, we can see that not all these electrons have the same kinetic energy. That's really, really important. So some of them have a maximum value. Those are the ones that are moving the most quickly, and some of them are moving a little bit more slowly. So what happens if I increase the intensity first of all? So if I make this ultraviolet light brighter, so we cannot see the photons, they're not shown on this animation, but there are more photons per second being shone onto the zinc plate. So there are more interactions between photons and electrons. So as we can see visibly, we get a greater number of electrons being released, and we can see the current has gone up. So that means we can actually measure how many more electrons are being released per second. Really important point, the maximum kinetic energy has not changed. So if I just go back to what it was before, I can lower the intensity. So I have fewer photons per second being shot onto the metal. I now have fewer electrons being released by the photoelectric effect, but the maximum kinetic energy of these electrons has not changed. That's a really important point. So what happens if I increase the frequency a bit further? So I'm going to increase to a higher frequency UV or lower wavelength, and we can see several things are changing. Well, we can see that we have more electrons being released and the current has gone up. So we can actually measure how many more electrons are being released per second. And we can also see visibly that they're moving more quickly. So the kinetic energy has increased. Now this is a really important point. So the kinetic energy, or the maximum Ke of the electrons released, is only dependent on the frequency of the light, not on the intensity. The intensity just affects the number of electrons, not the maximum kinetic energy. To recap the key points that we've just seen, strong red light is less effective than weak violet light. Something called the threshold frequency is the minimum frequency for this to happen. The current shown on the photocell circuit is a measure of the electrons released. Increasing the frequency increases the maximum kinetic energy of the electrons. Increasing the light intensity increases the number of electrons, but not the maximum kinetic energy. So we're going to put all of this together and look at a quantum explanation of this process. Okay, let's consider an explanation of all these effects that we've seen. So we're going to imagine that the electrons in the metal are in a well, in a potential energy well, so they require some energy to release them to the surface. Now this is a very simplistic view of the electrons in a metal. So we're just going to imagine that all the electrons are in layers. The ones at the top represent the outermost electrons in the atoms of the surface of the metal, and then lower layers are those electrons which are more difficult to remove, so deeper inside the atom or deeper inside the metal. So we have a photon of energy. It comes in and it transfers all of its energy to a single electron. So that's very, very important. We have a one-to-one interaction. Now this amount of energy here, called the work function, given the symbol phi or phi, that's the minimum energy needed to remove a single electron from the surface of the metal. So if the energy of the photon is bigger than the work function, then the electron will be removed and we'll have an excess of energy, some remaining energy, and that will appear as kinetic energy. Okay, so we have this interaction of energy, conservation of energy. So how are all these terms related? So we have HF, which is the energy of the photon, is equal to phi, the work function, plus the kinetic energy, half mv squared. Now it's important to say that's the maximum kinetic energy, and we'll see why that's the case later on in the video. So all of these terms must have the same units. They can all be measured in joules, typically. And it's also true that this will be balanced if they're measured in eV electron volts. But if we're doing any calculations with velocity, then we need to make sure that they're in joules. So we've got two definitions here. We've got the work function, the minimum energy needed to remove an electron from the surface of the metal, and the threshold frequency, which is obviously related to that. That's the minimum frequency needed to remove the electron from the surface of the metal. Let's look at some calculations with this formula. So if you want to pause the video and have a go at these yourself, that might be a good idea. So let's have a look at the first one. What will be the maximum kinetic energy if the energy of a photon is 6 eV and the work function is 4 eV? Now this is one of the benefits of using electron volts because the numbers are nice and simple. So hopefully you can see that if we rearrange the new formula we have to make Ke max the subject, then that's equal to HF minus the work function. So 6 minus 4 is 2 eV. So this idea of maximum kinetic energy, we cannot get a greater kinetic energy than that. But what about if we looked at an electron a little bit deeper inside the material? The work function doesn't change, but maybe the next layer of electrons requires 5 electron volts to release the electron to the surface of the metal, in which case 6 minus 5 will give us 1 EV. So some of those electrons will have a slightly less kinetic energy, maybe 1 electron volt. Maybe the next layer of electrons would require 6 electron volts to remove them just to the surface where they're just sitting there, because 6 minus 6 would give us 0. So we've got a range of kinetic energy all the way from 0 up to a maximum of 2 eV. To actually do a calculation of velocity, then we need to work in joules. So we can calculate in question 2, we've got the frequency, and we know the Planck constant, so I can calculate the energy of a photon in joules. I can rearrange the formula as we did before to find the Ke max. So that's equal to the energy of a photon take away the work function, which is 6 × 10⁻⁹, and that will give me 3.9 × 10⁻⁹. So I can calculate the kinetic energy, the maximum Ke, in joules. For part 2, we need to find the electron velocity. So half mv squared, I can rearrange to make v the subject, put the numbers in, and we should get a large value. And as we found in the previous video, expect big numbers for the velocity of an electron. So 10 to the 5 sounds about right. It could be 10 to the 6 or even higher. So we also need to consider a graphical representation of the photoelectric effect formula as shown here. So if I rearrange this to make E max or Ke max the subject, that's equal to HF minus phi. Then if I compare that to the standard formula for the equation of a straight line, y equals mx plus c, what that means is I'm going to plot the kinetic energy, the Ke max, on the y-axis. I'm I'm going to plot on the x-axis the frequency, shown here, and then the gradient would be equal to h. So if I worked out the gradient of this line, it would be equal to the Planck constant. The y-intercept is always going to be negative, and the y-intercept will be the work function. This is a very typical exam question. You might be presented with a question like this, and you have to either calculate a value for the gradient, which should be equal to the Planck constant. They might ask you to read off the values. So the y-intercept would be equal to the work function, and we can ignore the minus. The x-intercept is the threshold frequency. Now if we apply this to what we've just been considering, the frequency can be any value that we apply. That's the frequency of the external light. If that is less than the threshold frequency, then the kinetic energy max is 0 and the electrons are not released from the metal. At the threshold frequency, they are released with 0 kinetic energy, and as I increase the frequency, the Ke max will increase, which is what we saw in the simulation earlier on in the video. We could also compare two metals, so I might have metal A and metal B. Metal B has got the largest work function because it's got the largest value, the magnitude of the y-intercept. It also has a larger threshold frequency. However, we can see that these two lines are parallel. They both have the same gradient. The gradient is always the Planck constant. This is the final thing we need to consider. What is the energy of the photoelectrons, the electrons released by this effect? So we looked at the photocell circuit earlier on in the video. And when we did that, we had 0 voltage applied. What we can do with this is actually apply a negative voltage between these plates. So the electrons are released from this plate here, and previously there was no voltage applied. If I apply this negative voltage, that is going to repel my negatively charged electrons. And if I keep increasing the size of that voltage, at some point these electrons will not be able to make it to the far electrode. So what we would find is, as we increase the negative voltage, the current is going to start decreasing from its maximum value until it becomes 0. So just as the point where it becomes 0, the voltage applied is called the stopping potential, because it's the potential difference which causes the current to stop, or the electrons to stop traveling all the way to the other side. At that point we record the voltage, and then we can just multiply that by the charge on one electron, and that will give me the work done in stopping the electron, which is equal to the kinetic energy. So a simple worked example: if I, for a particular photocell circuit, a particular light and a particular metal, if I increase the voltage till it becomes large enough to reduce the current to 0, and I record that value, it's minus 1.2 volts, I can calculate the maximum Ke of the photoelectrons. And in this case, it's a nice simple calculation. The Ke is equal to the work done, which is equal to Q times V, the charge on one electron multiplied by 1.2, and we can calculate the maximum Ke of those photoelectrons. Right, we've made it to the end of the lesson. So this is really difficult stuff. Very often my students find that this is one of the most complex and mentally demanding lessons of the course, certainly in the first year. So just as a quick recap, we've looked at the photoelectric effect in detail. We've defined the work function and the threshold frequency. We've used this formula to calculate the maximum Ke and therefore the velocity of the photoelectrons. We've looked at a graphical representation of this formula, and then we've considered the kinetic energy of the electrons and how that's related to the stopping potential. So well done for working through this full video. The next lesson I recommend you watch is the third one in the series, which looks at wave particle duality and the de Broglie wavelength. That should be D, not B. See you next time.